Introduction to Computing. Chapter 9, Computer System Organization and Architecture. Introduction. Lesson introduces the difference between computer organization and architecture, which is the study of internal working, structure implementation, a computer system. It also includes the functional view of the von Neumann model and the number system, which is fundamental to understand how computers will be also presented to demonstrate on how to convert number systems. Exercises will be given at the end of the lesson to give the students time to practice before taking the assessment task. Learning outcomes. By the end of this module, student will be able to define and discuss computer organization and computer architecture, identify the different units of measure common to computers, discuss and explain the components of von Neumann architecture and the function of basic computer components, and computer number systems for its equivalent representation. Learning content. To have complete understanding of computer system, it is very important to study both hardware and software design of several computer components. It means that each functionality has to be considered in order to increase the performance of the computer. Computer organization and architecture mostly focuses on the different parts of the computer in order to lessen the execution time of the program and improve the performance of each part. Usually, people think computer organization and computer architecture is the same, but there is a slight difference. The difference between computer organization and computer architecture are: computer organization is the study of the system from software point of view and overall description of the system and working principle without going much detail. In other words, it is mainly about the programmer's user point of view. Computer architecture is study of the system from hardware point of view and emphasis on the system is implemented. Basically, throws light on the designer's point of view. Architecture versus organization. Computer architecture is considered with structure behavior of computer. Architecture, logical design of a computer allows you to write programs. Instruction set, representation of data types, integers, characters, floating point of types. Input and output mechanism. How does the computer communicate with the world? Memory addressing techniques. While computer organization, it is concerned with interaction with computers. Organization, physical design of a computer. How many registers? What is a registers? How many registers have the CPU have? Computer organization refers to the optional unit and their interconnections that realize the architectural specifications. Hardware details to programmers involves the studying the major functional units of a computer and how do they work. Attributes of computer organization. Control signals. A pulse or frequency of electricity or light that represents a control command as it travels over a network. A computer channel or a wireless. In the data communication worlds, control signals typically travel the same path in the data, either as separate packets or contained with the data packets. Computer peripheral interface. Peripheral is a device that is connected to the host computer, but not part of it. It expands that host capabilities but does not part of the core computer architecture. While interface is the point of interactions with software or computer hardware, or with peripheral devices such as a computer monitor of a keyboard. Some computers interfaces such as a touch system can send and receive data, while others such as mouse or microphone can only send data. There are two types of interfaces. Number 1, hardware interfaces. Computing systems between many of components such as the various storage devices or I/O devices and etc. While software interfaces refer to the range of different types of interface at different levels. An operating system may interface with pieces of hardware. Memory is the collection of storage unit or device together. Computer architecture is the specification detailing how a set of software and hardware technologically standards interact to form a computer or platform. Refers to how computer system is designed and what technologies it is compatible with. The functional behavior of a computer is viewed by a programmer. The theory behind the design of computer. Other definition, the design of integrated system which provides a useful tool to the programmer, the study of the structure behavior of and computers. The design of the system specification at a general or subsystem. The art of designing a machine will be pleasure to work with. Therefore, computer architecture refers to attributes of a system visible to programmers, attributes that have a direct impact on the execution of programs. Mas mapabilis nito ang pag-execute ng paggawa ng program. Attributes of computers architecture. The ISA, or it means Instruction Set Architecture, is a part of a processor that is visible to the programmers or compiler writer. Serves as the boundary between software and hardware. Data representation refers to the methods used internally to represent information stored in a computer. Computers store lots of different types of information, text. I/O, it means input and output mechanism. The communication between an information processing system. Addressing techniques are an aspect of the instruction set architecture in most central processing unit or CPU design. The overall explanation of computer organization and computer architectures are both important in understanding how a computer works. Computer organization focuses on how a computer is physically built, how its components work together. It deals with the implementation of the computer system, hardware. It is concerned with internal operations such as control signals, computer peripheral interfaces, hardware, and software. While computer architecture focuses on logical design and behavior of a computer system, kung paano sila gumana at mag-run ng maayos. It describes what the computer can do from the programmer's point of view. Dito nila dinidescribe ang computer kung paano gumana ito at makita natin sa kung paano mag-run ang system sa ating point of view. It includes instruction set of architecture, the ISA, and the data representation and the I/O, and the addressing techniques. The difference between architecture and computer organization is what the computer does on the computer architecture designed and the futures of visible to programmers, while computer organizations, how the computer does it. It is a physical components and their connection. And the overall, fully understand the computer system, and you must study both computer architecture and computer organizations so they can help improve a computer's performance, efficiency, and functionality.
Alright, so thank you so much to our first presenter. And now before we move on to our next segment, allow me to briefly introduce myself. Good day everyone, my name is Geisa Anpiambros and I am currently a first year student taking a Bachelor's of Science in Information Technology with specialization in web and mobile applications development, and I will be your presenter for this next segment. And with that out of the way, let's now actually get into our next segment where we will be tackling 4 topics of discussion, which are of course the function and structure. There's also the function view of the von Neumann model, and the system bus, and of course the motherboard. So let's start with our first topic, which is, as you can see here, the function and structure. But before we actually discuss what a structure is, what a function is, and what they do, let's first briefly talk about what a computer is. Now, as you can see here in the presentation, a computer is an electronic machine that takes data as input, processes it using instructions, stores the information, and gives a useful result as output. Now, that is actually a simplified description of what a computer is, because as we know, a computer is a very complex system with a lot of work going on behind the scenes to actually make the computer work. Hence why developers often ask, how can we describe or design it to make it easier to understand? And aside from that, I would also like to mention that a computer has a hierarchic system, which according here in the module is a set of interrelated subsystems with each subsystem hierarchic in structure until some lowest level of elementary subsystems is reached. Or in simpler terms, it's like a Russian nesting doll. Now, if you're unsure what a Russian nesting doll is, I actually don't have one at hand right now, but I do have these pieces of paper. Now, this bigger piece represents the bigger doll, aka the doll that houses all the other dolls. And when you remove the top of the doll, you get another doll, smaller this time. Then, get another doll, another doll, another doll, and it just keeps going until you reach the smallest doll in the pile. And that's basically what the module is implying a hierarchic system in a computer is like. So anyways, moving on, as we mentioned earlier, a computer has a hierarchic system. And within this hierarchic system, there are two main aspects that should always be considered, which are, of course, the structure and the function. With the structure being the way in which components relate to each other or how each component work together inside the system, and the function being the operation of individual components as part of the structure. So the function is the one that makes sure that everything goes well, everything does what it's supposed to do. And take note of this, a structure is not complete without a function, and a function can't operate without a structure. So these two components are interrelated. They cannot operate without one or the other. Now also we have here under function, we have four basic computer functions, with the first being data processing, which is responsible for the collecting and manipulating of raw data in order to create useful information. So we can actually relate this to how cooking or baking works, where you take raw ingredients, you mix them, you cook them, you put them all together to create a full dish or a complete dish or a complete pastry or baked good. Then of course we also have the data storage, which is already pretty self-explanatory. This is the one responsible for archiving data in electromagnetic or other forms for use by a computer or device. And now if you're unsure what electromagnetic is or what electromagnetism is, this is actually the process where electricity and magnetism work together to save data. So there's that. And of course, under basic computer function, we also have data movement, which it says here is the one responsible for how the computer interacts with the outside world, and it also ensures that data's accessibility to devices outside the computer is met. Or rather, in simpler terms, this is how the computer processes and displays itself. And under data movement, we have two types, which is the peripheral and data communication. With peripheral referring to the data transfer between CPU or RAM and external hardware devices such as the USB, HDD, memory disk, etc., etc. And we, of course, also have data communication, which is the transfer and flow of data from one place to another. And of course, last but not the least, we also have control under the basic computer functions, which is the main operator of all the basic computer functions. So control is the one that ensures that every single one of the basic computer functions do what they are supposed to do. So now we move on to the function view of the von Neumann model, which is a model founded by John von Neumann, a mathematician from 1945. And in this model, in simple terms for easier understanding, is a one-lane model because everything goes into one single bus and runs only in one lane, which we will see here as we talk about the 5 major components of the von Neumann model, which are the input unit, output unit, the arithmetic logic unit, the memory unit, and the control unit. So let's first start off with the input unit. As we can see here, it is the getting of information into the computer. So examples of this are keyboards and mouse. And we also have the output unit, which is the opposite of the input unit because it gets information out of the computer. So for example, a printer or a monitor. Next up, we have the arithmetic logic unit, or the ALU, which carries out the arithmetic and logical operations, or in simpler terms, is a built-in calculator inside the processor. Next up, we have the memory unit, which again, is already pretty self-explanatory. This is the storage unit for the system. And of course, lastly, we have the control unit, which, as you can read here, ensures that each component does their task correctly at the correct time. So actually, you can akin this to a supervisor, as the control unit ensures that every single part of the model, every single unit, does what they are supposed to do. So that's the function view of the von Neumann model. Let's now move on to the system bus model, which is a more refined version of the von Neumann model. As in this model, there's 3 types of buses and 3 lanes that each unit goes through. So it doesn't just go in one lane like in the von Neumann model. So here in the system bus model, as you can read, it is a shared pathway for communication among components. And there are also 4 parts to the system bus model. First, we have the data bus, which, as you can read here, is a connector or set of wires within a computer or device that transport data. Or in simple terms, this is where the actual information goes through. And then we also have the address bus, which again, as you can read here, is a computer bus architecture used to transfer data between devices that are identified by their physical address. Or again, in simpler terms, this is the bus that navigates and guides where the data bus should go to deliver the information. So next up, we also have the control bus. As we can read here, it is a computer bus used by the CPU to communicate with the devices within the computer. This can also occur through physical connections. So again, like the control unit in the von Neumann model, this bus is the one responsible for making sure that the data bus and address bus does their work correctly. And lastly, we also have the peripheral bus, which is also known as the I/O or input-output bus. And this is the data pathway that connects peripheral devices to the CPU. So in simpler terms, again, this is where data goes back and forth between a computer and an external device, whether that be a keyboard, a mouse, etc., etc. And if we move to the next slide, we have here the system bus model, what the system bus model looks like. And we have here the CPU, which holds the ALU, the registers, and the control. We also have the memory and the input and output. And as you may notice over here, each one of them goes through every single bus because every single bus has their own task. Not everything is put on the data bus, not everything is put on the address bus. Each of them has their own task, with the data bus carrying the information, the address bus carrying the location where that information is supposed to go through, and the control bus being the one that makes sure that all that information goes to where it's supposed to be. And lastly, for this segment, of course, we have the motherboard. And as you can read here, the motherboard is a printed circuit board that contains the main components of a computer or device. So this singular rectangle is the one thing that's powering your computer right now or your device right now to make sure that it functions the way it should. And now, as you can see here in the presentation with the model of the motherboard, we have the input-output, the ALU. We've already talked about this earlier. And we also have the power supply connector, which powers internal components. We also have the memory, the battery, and the plug-in expansion card slots, which if you want more features or better performance, you can just slot in cards in there to get those features and to get better performance. And within the motherboard, we have two chips which is in the core logic chipset of a PC motherboard, which are the North Bridge and the South Bridge, with the North Bridge being the controller that interconnects the CPU to the memory via the front side bus. It can also connect the peripherals through high-speed channels. And of course, we also have the South Bridge, which implements the slower capabilities of the motherboard. And to better understand what the North Bridge and South Bridge are, we can actually compare this to how a theater production works, with the CPU being the director, the North Bridge being the stage manager, and the South Bridge being the background crew. Now, why is the North Bridge the stage manager? Well, it's because, as we mentioned earlier, this chip is more so focused on high-speed operations, and it also works together with the CPU to ensure that the overall performance goes smoothly. And why is the South Bridge the background crew? Well, this because the South Bridge handles all the slow background work behind the scenes to ensure that the North Bridge and CPU mainly focuses on delivering high-speed operations, as I said earlier, and to ensure a smooth performance. We also have additional information on the system bus here, which, as you can read, is a pathway composed of cables and connectors that carry data between the computer, microprocessor, and the main memory. Now, why is the system bus being brought up here again? Well, it's because the system bus is connected to the CPU along with the main memory. And as I repeat earlier, it carries data between the computer, microprocessor, and the main memory. This is also related to the omnibus, which is commonly referred to as a bus that carries lots of passengers, as we described earlier when we saw the system bus model. We have the data bus, the address bus, and the control bus. And we also have here, it connects to the CPU, to the main memory, and in some systems with the level 2 L2 cache. And of course, next up we have, again, the three main buses: the control bus, the address bus, the data bus. The control bus determines the data processing, the address bus determines where the data should be sent, and the data bus carries the data in need of processing. And right next to that, we have the motherboard diagram, of course, which in order, the South Bridge, North Bridge CPU, because as you can see here, the South Bridge is at the very bottom because the South Bridge reports directly to the North Bridge, while the North Bridge reports directly to the CPU. And what I said earlier, here how we can compare the South Bridge, North Bridge CPU to a theater production. You can see now here we have the memory slots, or the RAM, and the graphics, which are the most important part of a computer, because of course the graphics is what shows up on your screen and what shows up in your monitor, and the memory, of course, is where all the data that you store in your computer goes. And the North Bridge is in charge of making sure that the graphics, the memory slots, or RAM works as intended by the CPU. And at the bottom here, we can see the South Bridge, which is connected to a lot of other buses. As you can see here, the PCI bus, the LPC bus. This is the background work that I was talking about. The South Bridge is the one that deals with all of this at the bottom, so that the North Bridge can focus only on the graphics and RAM to report directly to the CPU. And that's it for this segment. Let's now move on to our next segment.
Now we move on to the digital components. The digital components consist of the first one, transistors. Transistors replace vacuum tubes in electronic circuits. They are smaller, cheaper, and produce less heat. They are invented in 1947 at Bell Labs by William Shockley along with his colleagues. Digital circuits are built from collection of logic gates which function as reusable components, and that is the transistors, the first one in the digital components. Now we move on to the second component, which is the microelectronics. Microelectronics means small electronics. Computers are composed of logic gates, memory cells, and interconnections. These components are manufactured on semiconductor materials such as silicon and wafers. And that is the microelectronics, the second component in the digital components. Now we move on to the third one, which is the ICS. ICS means the levels of integration. And integrated circuits are classified depending on how many logic gates they contain. Here we have the four types of integration. The first one is the SSI, small scale integration, that has 10 to 100 gates. The second one is the MSI, or the medium scale integration, that consists of 100 to 1000 gates. The third one is the LSI, or large scale integration, that consists of 1000 to 10,000 gates. And the last one is the VLSI, or very large scale integration, that consists of more than 10,000 gates. Now we move on to the data representation. Computers represent all data binary from zeros and ones. Data includes letters, numbers, symbols, and control characters. Coding systems convert these characters into binary so computer can process and store them. And that is the data representation. The next one is the famous coding system that has been used for data representations are, the first one is the American Standard Code for Information Interchange, or in short, ASCII. This is the most widely used characters encoding in personal computers that uses 7-bit binary to represent characters. An optional 8-bit may be used for parity checking of device-specific functions. And the next one is the extended binary code, the decimal interchange code, or EBCD, developed by IBM for its larger computer systems. It uses 8-bit binary to represent characters, and it supports 256 characters. It uses different character codes from ASCII and is now used mainly in legacy IBM systems. And the last one is the BCD, or the binary coded decimal. This represents each decimal digit using 4 binary bits. Only binary values are 0000 to 100, 1001, and 0 to 9 are valid. And that is the famous coding system that has been used for data representation.
Types of number system. Decimal system. The most commonly used number system by people. It uses the digits 0 to 9 and has a base of 10.
Decimal system ay ang base niya ay 10. At ang pwede niya lang gamitin na digits ay 0 hanggang 9. And then move ka sa binary system.
Binary system. Used by computers, it uses only 0 and 1, called bits or binary digits, and has a base of 2.
Yun. Based sa sinabi niya, ang binary system naman, ang kanyang base ay 2 at ang kanyang pwedeng gamitin lang na number ay 0 to 1. And then sa octal system naman.
Octal system, a shorter way to represent binary numbers. It uses the digits 0 to 7 and has a base of 8.
And then, based sa kanyang pangalan, octal means 8. Kaya ang kanyang base ay 8. At ang kanyang pwedeng gamitin na digits ay 0 hanggang 7.
Hexadecimal system, a compact way of representing binary values. It uses 0 to 9 and A to F, where A to F represents 10 to 15 and has a base of 16.
While sa hexadecimal system, ang kanyang base naman ay 16 kasi nagmumula sa kanyang pangalan na hexa means 6 and then deci means 10. 6 plus 10 equals 16. And then ang kanyang mga gagamiting digits naman ay 0 to 9 yung number, and then sa alphabetical ay A to F kasi kapag nag-10 na pwede mo nang palitan ng A, and then 11 B, and then 12 ay C hanggang sa F.
Number system conversion. To convert decimal to any system, repeated division by the new number system-based technique is used. The steps are as follows. A. Divide the decimal number to be converted by the new base. For example, divide 2 for binary, 8 for octal, and 16 for hexadecimal. B. Write the remainder on the right side. C. Repeated the process until the quotient is 0. And D. Collect all the remainder starting from the last quotient going upward.
For example, magko-convert ng decimal to binary. Pag naririnig mo yung decimal, ang tanging operation na gagamitin mo lang ay division. Like this, 74 over 2 equal 37, remainder 0. Pag odd number ang lumabas, automatic, ang yung remainder ay 0. And then, ito naman, odd ay even number, 37 divided by 2 equals 18, remainder 1. Ibig sabihin yung value ng even ay 1. Ano ba ang mga even? Like 2, 4, 6, 8, 10. And then, ang mga odd naman ay 1, 3, 5, 7. And so on and so forth.
And that's all. Maraming salamat po.